Low Earth orbit satellites have a unique need for error correction due to their proximity to the radiation of space and the transmission between the ground and the atmosphere. Probability of single bit, multi-bit, or block burst errors in communication and memory due to error events are raised as a result of this location. Combinations of forward error correction and error correction schemes combined with erasure mending methods offer more novel solutions for error correction in satellites. In this, I'm going to review several different error correction codes and some of their applications in satellite subsystems of error correction. That'll be block Hamming codes, block turbo, low density parity check or Gallagher codes, as well as future machine learning implementations and interleaving. These are codes that were created in the early 1950s. They were used for small sections of error correction. You can see that you have some sort of input, and then you have segments of parity that are checked within certain boundaries of whether the option is even or odd. Some of the implementations that scientists have used so far through FPGAs is something where they encode a segment of data and then they decode that segment using the Hamming algorithm. It's probably the best situation for most low Earth orbit satellite configurations because there aren't any large sets of physical data that are being switched from radiation. Pictured here are both the encoder and decoder in terms of a sort of synthesized RTL view. You can see the actual XOR gates and sections of muxes, and then there on the decode side you can see two different muxes that select the single error correction or double error detection, and this would be easily implemented in a satellite FPGA. Another methodology that engineers use in satellite error correction is low density parity codes. These are actually little linear error correction codes that we already use in digital television, so things like DirecTV. They work in a way of belief propagation, so the process of passing a message using sort of an inference or like a sum product. It has a sort of form of a factor graph node as represented below, and it's a little bit complicated, but you essentially use a generated matrix from your original code word matrix, and you check and see after your operation if it's orthogonal. It's mostly been used in satellite transmission for the past 20 years, as well as it's been used in a lot of Wi-Fi and Ethernet standards. The final error correction code I wanted to talk about was block turbo codes that their patent got finally released in 2013. It's been used in very many applications between low Earth orbit satellites and other applications that are further away from the Earth. So you'll find them in missions like Cassini or Pathfinder. The difference between block turbo codes and low density parity checks is the fact that you have a far larger amount of bandwidth efficiency. So you'll often see implementations of it with very well-designed access methods. Pictured here is two decoders and an interleaver for some sort of physical process for the actual hardware. It works with those two decoders in a convolutional method to generate likelihoods so that the pattern bits differed and sort of compare the differences. I also wanted to talk about interleaving, which is sort of just burst distortion. You can see that when you send a message fully with no interleaving and you have a sort of burst distortion, then you see that information is lost in large blocks instead of small pieces. There are potentials with machine learning as well. Many engineers are currently working on different ways to incorporate machine learning into both the transmission and detection of errors in forward error correction. Some of these are relatively complex systems that involve lots of different matrix factorizations and a lot of specific statistics revolving around data clustering and filtering for the actual optical transmission of data. The field of error correction needs to balance a lot of different things in consideration of where exactly the satellite is orbiting, as well as what specific methods need to be used. Specifically for a lot of low Earth orbit error correction, it seems that mostly simple parity checks work for now and are a bit more efficient for FPGAs and for those actual engineers creating it. Since it's relatively safe in the Van Allen belts, memory is mostly protected, but as far as transmission between the ground and satellites through an atmosphere, some methods of forward error correction may be needed for those actual transmissions.